Okay, so I think we're ready to move on from considering our conjugate eye movements to a discussion of our disconjugate eye movements. And what we have in mind here are called vergence eye movements, and there are two varieties of vergence eye movements. There's convergence and then there's divergence. So imagine the situation where you are changing your fixation from some point at some distance away from you towards a near point. So maybe you're looking off in the distance and you decide now to hold up your finger and look at what might be on the end of your finger. When you do that, you're changing fixation from, let's call it point B to point A. And such a change in fixation is going to involve a rightward rotation of your left eye and a leftward rotation of your right eye. So both eyes are in adduction. And so this is activity that's driven by the ocular motor nerve, causing contraction of the medial rectus muscles in both orbits. And so that's what's necessary to go to a near point of fixation. Now, if one was going to go from that near point of fixation to a distant target, divergence is necessary. So divergence is going to cause the left eye to rotate to the left and the right eye to rotate to the right. This will bring our point of fixation from point A out to some distant target, point C. Okay, so going from near to far involves divergence. So you can imagine that there is likely to be a different kind of circuitry involved with different kinds of internuclear connections that allow for the coordination of the activation of the medial rectus and lateral rectus muscles as we go from a near target to a far target. So how are such movements organized by the nervous system? Well, we won't answer in depth for all kinds of eye movements, but I do want to give you a bit of a feel for the organization of circuitry that helps to coordinate the output of our brainstem ocular motor nuclei to govern these 6 pairs of extraocular muscles. And I want us to consider really 2 aspects of the challenge of moving our eyes. One is to produce the correct amplitude of movement, and the other to move the eyes in the appropriate direction for whatever the challenge might be. So concerning amplitude, the amplitude of movement of the eyes is encoded in the rate and duration of activity in the appropriate alpha motor neurons. So this is illustrated in the panel here to the left. So imagine that we want to shift our eye position from, let's say, more or less straight in front of us, off to the left. Well, for the left eye, let's call this the left eye, that's going to require activation of our lateral rectus muscle. So the lateral rectus muscle is going to contract, and that's going to allow the eye to rotate towards the left, or to abduct, Okay, so now if we are recording from the alpha motor neurons that innervate that lateral rectus muscle, what we find is that these motor neurons start firing action potentials just as we're beginning to actually contract that lateral rectus muscle. And very soon after the onset of contraction, within just a few milliseconds, there is an adjustment in eye position. Now, if we're just making a very small deviation from our neutral resting position, then that motor neuron might go quiet again. But if we want to continue to move further and further out to our left, we will need to induce another burst of action potentials in this abducens motor neuron. That's going to cause this eye to deviate even further. And now if we get beyond some critical distance where we actually need to pull our eye in order to keep fixation at that particular angle relative to the neutral position of our orbit, there may be some ongoing activity in that abducens motor neuron. Let's say we now make a far extreme eye movement, abduction, moving our eye out far to the left. Now another barrage of action potentials is needed, but so will a higher rate of sustained activity in order to keep that eye pulled off to the left. We need to contract that lateral rectus muscle in order to prevent the eye from being pulled back or relaxing back to its neutral position. Now notice what happens if we were to make a eye movement back in the opposite direction, in the direction of adduction towards the midline. This abducens motor nucleus neuron will go silent during that period, and this reflects the activity of some kind of interneuron that will suppress the activity of this abducens alpha motor neuron. In this way, the signals that are coordinated between the motor neurons that adduct the eye and abduct the eye can be coordinated, and they can work in synergy with one another. So when the eye is adducted, adducted, the abducens neurons fall silent, and vice versa for the ocular motor neurons that innervate the medial rectus muscle. Now, what about direction of movement? Well, direction of movement can be a challenge in various ways because objects of interest that we might want to look at can happen really in any position relative to our head in our frame of reference. So we need the ability to integrate signals that will allow us to direct our eyes towards any location in the visual world. And so part of the solution to this challenge of directing our gaze at an object of interest has to do with the biomechanics of the extraocular muscles. So we have these 6 pairs of extraocular muscles that have particular actions. They rotate the eye around particular axes of rotation. Part of this challenge is solved by simply coordinating the appropriate pairs of extraocular muscles. So the direction of motion, then, is specified by which pairs of extraocular muscles are activated. These muscles are coordinated by circuits of interneurons that are found in the core of the brainstem in this structure that we've been talking about from time to time as the brainstem reticular formation. Well, as I've said elsewhere, the reticular formation really isn't one structure. It's really a large collection of circuits. And there are a couple of circuits that I would highlight here. And these are circuits that coordinate the horizontal movements of the eyes and the vertical movements of the eyes. And what's illustrated in figure 20.8 is the circuitry that coordinates the horizontal movements of the eyes. And that circuitry in the reticular formation is known as the PPRF, and that stands for paramedian pontine reticular formation. And one way to think about this circuit is a set of interneurons that are integrating signals that may be command signals from other motor structures, or they may be sensory signals. And the output of this circuitry of interneurons is to coordinate the appropriate firing of abducens motor nucleus neurons and ocular motor nucleus neurons that govern the lateral and medial rectus muscles respectively, so that our eyes can move in a conjugate fashion along the horizon. Okay, well, suppose I want to look off to my right. Imagine I'm just going to look to see if someone's over there, or maybe to see what time it is on a clock on the wall. That's going to require the abduction of the right eye, moving out laterally away from the midline, and the adduction or the adduction of the left eye. For the right eye, the lateral rectus muscle needs to contract, and for the left eye, the medial rectus muscle needs to contract. Well, here's the circuitry in the brainstem that makes this possible. I want to look towards the right, so there are circuits in this right paramedian pontine reticular formation that will drive the output from the right abducens nucleus, and that's going to cause the contraction of the right lateral rectus muscle. There will also be an internuclear neuron that will cross the midline and supply the appropriate alpha motor neuron in the contralateral ocular motor nucleus. That motor neuron then will fire away and cause contraction of the left medial rectus, allowing me to turn both eyes to the right in a conjugate way. So again, this paramedian pontine reticular formation is what we call the horizontal gaze center. Now, not illustrated here is another gaze center that's actually present up here in the midbrain. and it's a gaze center that coordinates vertical eye movements, okay? And we simply call this the vertical gaze center. And like the paramedian pontine reticular formation, the vertical gaze center is a network of interneurons that will coordinate the output of the appropriate motor neurons in the oculomotor nuclei that are governing the superior and inferior rectus muscles. And there's probably also some input to the trochlear nuclei to govern the superior oblique, as well as to the alpha motor neurons in the oculomotor complex that govern the inferior oblique muscles. Those four pairs of muscles together are responsible for moving the eyes upward and downward.